Rational functions have asymptotes. So first I'm going to talk about what actually an asymptote is. So an asymptote is a line that a graph approaches but never intersects. We'll talk later where there's sometimes there's a little bit of an exception to that rule, but basically the graph can never intersect it. So what is a vertical asymptote? Well, a vertical asymptote is a vertical line that a graph approaches but never reaches. So the way we define it, we say is x approaches some number c if my rational function r approaches infinity. Then we say the line x equals c is a vertical asymptote. So think about this, because when is this going to happen? Well, when x approaches 0, what does 1 over x do? 1 over x is going to infinity, because as you have a very small number on top, it becomes very large because it's the inverse of it. So this we say is undefined, because you can never divide by 0. So when r of x is defined as p over q, what we're really looking for is when is q equal to 0, kind of like we looked at the domain. So we found the domain. We go back to the examples we had before, right? We had an example of x squared plus 5 over x minus 3, and we said x couldn't equal 3. So it turns out since x minus 3 is where it's undefined, where it equals 0, we say our vertical asymptote is at x equals 3. Also, what we need to think about is which way it approaches. So if I look here, as x is approaching 3, right, what's happening to this? Well, when it's a little bit less than 3, is it getting to 2, 2 minus 3, that's negative 1, right? So there's a vertical asymptote here, but on the left side, it's going to negative infinity. But if I'm a little bit bigger, let's say 4, so we have 4 minus 3 we're dividing by, that's positive 1. So what happens that on the right side, it goes to positive infinity. And as it turns out, if you have an even multiplicity asymptote, it's not really multiplicity, but if you talk about that as an asymptote, then they both go positive or negative infinity, but they both go in the same direction. But if it's odd, like in this case where I have just 1, then one is positive infinity and one is negative infinity. So my next example, here I have this. It's a little bit different. So what I want to do first always is I want to simplify if possible. So I have x minus 2 on top, and x squared minus 4 is the difference of 2 squares. So that's x minus 2 times x plus 2. And look what happens here. I have an x minus 2 on the top and the bottom, and they cancel out. So that tells me that this looks like 1 over x plus 2. But if I look at the domain first, the domain would be all x, such that x can't equal 2 or negative 2. But in this case, I got rid of that 2, so the only place I have a vertical asymptote is here, which is when x equals negative 2. So that's my vertical asymptote. So what happens to positive 2? Well, we call this a removable discontinuity. And we also call it a hole. There's a hole in the graph, and that's because it cannot equal 2, but I can reduce it so there's not an asymptote.